Our next topic is going to be membrane transport. Membrane transport is very important. Your plasma membrane is going to act like a barrier, but there is a continuous traffic across the cell membrane because nutrients have to get into the cell in order for the cell to be able to provide energy and products. And then those products and wastes must get out of the cell. So membrane transport is very important to cell function. Membrane transport depends on permeability. The permeability of a plasma membrane determines what substances are allowed to move into or out of a cell. And our permeability comes in a range. We have 3 different categories, 2 extremes and then 1 middle of the road. Our first extreme is going to be an impermeable membrane. Impermeable membranes do not let anything cross. Nothing is allowed to move into the cell. Nothing is allowed to move out of the cell. It is a staunch Berlin Wall. Our second extreme is a freely permeable membrane. Freely permeable membranes will let anything pass across the membrane. Solutes, water, ions, whatever you want, has a free pass to move across the membrane. And then finally, our middle of the road category is a selectively permeable membrane. A selectively permeable membrane will let some substances pass, and it will restrict the movement of other substances. So it selects which substances are allowed to move across the membrane. Now, as I said, we have a range of permeability throughout our entire body depending on the specific function of that cell. However, the majority of our cells are going to be selectively permeable, and so when we talk about a cell, you can assume that it is going to be selectively permeable, and then we will learn the special cases of cells that are either impermeable or freely permeable. As we talk about membrane transport, we need to revisit the vocabulary of a solution. Remember, a solution is a mixture of a solute and a solvent. The solute is the substance that is being dissolved. We like to talk about salt being dissolved, so we frequently talk about sodium being our solute. Potassium is going to be another common solute, as well as glucose. So those substances are being dissolved, and our solvent is going to be our fluid. Most frequently in the body, our solvent is going to be water. So our water plus our solute is going to make a solution. Okay, so plasma membranes, in general, we can consider them to be selectively permeable, meaning they allow some material to move freely across the membrane and other material is restricted. We restrict movement of material based on that material's size. So if you think about the molecule glycogen, remember glycogen is a very large molecule. It is a string of glucoses, and that glycogen is not going to be able to pass across the membrane. But something much smaller, like glucose, just 1 6-carbon ring, that is going to be able to cross some of our cell membranes. So we can restrict movement based on size. We can also restrict movement based on electrical charge. The inside of our cell is going to have a more negative charge than the outside of our cell. So negatives repel negatives. So it may be more difficult for a negative ion, called an anion, to pass into the cell than it would be for a cation, a positive ion, to pass into the cell. Materials are also restricted based on molecular shape. Some materials cannot cross the membrane by themselves, but they can have help from proteins in the plasma membrane. Proteins are going to work just like enzymes do, because enzymes are proteins, and they're going to have that lock and key specificity. So we can restrict movements based on molecular shape. If your molecular shape matches a transport protein, you get to move into or out of the cell. But if it doesn't, then you're stuck on one side or the other and you're not moving. Finally, we can restrict movement based on lipid solubility. That is the ability of a substance to dissolve into a lipid. If something is lipid soluble, it will move through our phospholipid bilayer very easily, and it will have no problem entering or leaving the cell. If something has a charge or is polar, so ions or polar molecules, they do not interact well with lipids, and they are going to be stuck on one side of the membrane or the other and not allowed to pass without help. So we can restrict movement of molecules across a plasma membrane based on size, electrical charge, molecular shape, and lipid solubility. The transport across a plasma membrane can either be passive or active. If something is passive, it does not require energy, meaning you do not need to use ATP to move the molecule across the membrane. This means that the molecule needs to move down its concentration gradient. Our concentration gradient is going to be the amount of solute in our solvent. Generally, when we have a membrane, we are going to have different concentrations of solutes on one side of the membrane from the other. During passive transport, the molecule is going to move from the side with high concentration down to the side with low concentration. On the other hand, our transport can be active. Active transport requires energy to move our solute across the membrane. That means we need to use ATP for the movement of substances across the membrane. And in general, this means that we are going to move the substance against its concentration gradient. If you are moving against the concentration gradient, you are going to move from the side with low concentration to the side with high concentration. So we can classify transport as either being passive or active. Other than that, our transport can be divided into three categories. Diffusion is a passive transport. Then there is carrier-mediated transport. Carrier-mediated transport can either be passive or active. We will explain this in a little bit. And then third, we have vesicular transport. Vesicular transport is going to be active. Before we talk about the details of each of these types of transport, we need to remember that all molecules are constantly in motion. This motion causes random mixing of our solutes inside of our solvent. We also need to remember concentration gradients. The concentration of a solute is the amount of solute in a solvent. And again, when we talk about membrane transport, we have a membrane separating two watery mediums. and we generally have more solute on one side of the membrane than we have on the other side of the membrane. So first we are going to discuss diffusion. Diffusion is going to be passive, meaning that our molecules always move from high concentration to low concentration. In general, diffusion is the mixing of molecules randomly. This acts to spread our solute evenly throughout our solvent. The general goal of diffusion is to eliminate concentration gradients. So, when a membrane is involved, our solutes move down their concentration gradient from a high concentration to a low concentration. When a membrane is involved, we have several factors that affect diffusion. The first of these factors is the distance the particle has to move. If a particle has to move a long way, then diffusion is going to be quite slow. But if a particle has to move a short distance, then diffusion is going to be faster. The way I think about this is the spread of a smell throughout different sizes of rooms. So when I was in graduate school, I was the teaching assistant for a mammalogy class. And we would take our students on field trips, and one field trip we caught a skunk, and I was so excited. It was awesome. We caught a skunk. It was so much fun. No one would go near the trap except for me. Me being the teacher, I had to get the skunk out of the trap. And luckily, I have worked in wildlife rehabilitation, and I knew that if you hold the tail of a skunk down, it can't spray you. So I successfully got the skunk out of a trap, did not get sprayed, held it up, was talking to the students about general characteristics of the skunk, and nobody would come near me because they didn't trust me, but that's okay because I had a good hold on the skunk and it was not going to spray me. So finally, we're done talking, and I went to go release the skunk, and I walked over to a bush. I turned the skunk sideways, I tossed it into the bush, and then I turned around and ran, and I did not get sprayed. But because I had handled the skunk, I smelled like skunk, and nobody wanted to ride home with me in the car. But my feelings weren't hurt because I knew that a car is a very small space, and it would not take long before all of those wonderful skunk scent molecules spread throughout the entire car because it's a small space. Whereas if I walked into a classroom, our door is in the corner of our classroom, so if I walk into the classroom, the students sitting nearest me are going to smell the skunk smell fairly soon. But then it's going to take a while for the person in the opposite corner to smell it, because there's a greater distance that those smell molecules have to cross in order for them to be evenly distributed throughout the entire room. So, long story short, the distance a particle has to move affects the rate of diffusion. Second, we have molecule size. Smaller molecules move faster than larger molecules. The way I like to think about this is thinking about the activity of small children versus the activity of their parents. If you have a 4-year-old, let's say, that 4-year-old has a lot of energy, and so the 4-year-old runs around the room while the parent sits in the middle of the room waiting for the toddler to come near them to play with them. So small molecules move faster than large molecules. Next, we have temperature. Temperature is actually the measure of motion in molecules. The higher the temperature, that means you have more motion. So more motion is going to lead to faster diffusion because our solutes are going to spread out throughout the entire mixture faster as they are moving faster. So lower temperatures, less movement, slower diffusion. Next, we have gradient size, the difference between concentrations across the membrane. If one side of the membrane has a very, very high concentration, there is going to be a lot of pressure for that solute to move down its concentration gradient to the other side that has a very low concentration. So big gradients mean faster diffusion. On the other hand, if we have two concentrations that are very, very similar, then there's not a lot of pressure for substances to move across the membrane, and diffusion is going to be much slower. So high concentration gradient difference means greater rates of diffusion. Finally, diffusion is affected by electrical forces. Again, the inside of the membrane has a more negative charge than the outside of the membrane. Opposite charges attract, so the inside of the membrane is going to attract positive ions, and like charges repel. So the inside of the membrane repels negative ions. Diffusion can be categorized as simple or channel-mediated. Simple diffusion means that materials are simply going to be allowed to move across the membrane whenever they want to, according to their concentration gradient. They do not have to stop at go. They just pass through the membrane with no help. They just do it. Materials that are capable of simple diffusion include lipid-soluble compounds. So remember, our hydrophobic tails of our phospholipids are what are actually forming the barrier of the plasma membrane. These hydrophobic tails are made out of fatty acid chains. Fatty acids are lipids. So if we have a substance that easily dissolves into a lipid, it can easily move through our hydrophobic tail barrier and get across the membrane either into the cell or out of the cell according to its concentration gradient. Lipid-soluble compounds include alcohols, fatty acids, and steroids. Also capable of simple diffusion are dissolved gases. Dissolved gases include carbon dioxide and oxygen. This is wonderful because our oxygen can move freely into our cell according to its concentration gradients and provide our cell with oxygen for aerobic respiration, which is used to make ATP. A byproduct of that aerobic respiration, so the waste of that process, is CO2. We don't need CO2, and so it can freely move across our plasma membrane to move into our bloodstream and then get exhaled from our lungs. So simple diffusion does not require any help to pass across the plasma membrane. Our substances simply move through the middle of our plasma membrane according to their gradient. Diffusion can also be channel-mediated. Channel-mediated diffusion means that our diffusion requires a transmembrane proteins. In order for it to be diffusion, it is going to be passive, and we are going to move substances down their concentration gradients, but these are going to be substances that need a little bit of help in order to do that. They can't just pass through the middle of the plasma membrane. They are going to pass through a protein. Water-soluble compounds and water itself and ions are generally going to use this channel-mediated diffusion. So as we talked about proteins before, the passage of material is going to depend on the size of that solute. Large solutes are more difficult to get across the membrane than small solutes. Our passage depends on the charge of the solute. So just as we spoke before, the inside of the membrane is more negative, and so it is harder to move negative ions into the cell than it is to move positive ions. And then the interaction with the channel is going to make a big difference. What we mean by this is the specificity in shape of the molecule in comparison to the shape of the transport protein. So you should be hearing a theme here for the use of proteins in transport of materials across the cell. We actually have 3 different types of channels that work in channel-mediated diffusion. We have leakage channels. Leakage channels are always open, okay? They allow substances to move across the membrane according to their gradient, but they only allow specific substances. So for example, you are going to have a sodium leakage channel. This allows sodium to move across the membrane according to its gradient, but it would not allow potassium to move through that specific channel. So they are specific, but they are always open. Next, we have gated channels. Gated channels are opened or closed by a specific type of stimulus. This stimulus can vary. We actually have 3 different kinds of gated channels. A chemically gated channel is going to open or close when a specific chemical binds to our transport protein. That is going to open up our channel, and then when the chemical unbinds, our channel will close. When the channel is open, it will allow any number of solutes to move across the membrane, but again, each channel is going to be specific to a specific kind of solute. Okay? Second, we have electrically gated channels. We call these voltage gated channels. These voltage gated channels are going to open and close when the electric charge across the membrane changes. These are going to be very important to action potentials when we get to that unit. And finally, we have mechanically gated channels. Mechanically gated channels are going to open and close in response to physical distortion of the plasma membrane. Okay, now, as I have been saying, our channel-mediated diffusion depends on proteins. These proteins exhibit specificity, so each channel is going to be designated to one kind of solute. Now, once that channel has opened, let's say we're talking about a chemically gated sodium channel. When that chemically gated sodium channel is open, many sodiums can move across the membrane at a time. It's not just one sodium, it's as many sodiums that want to move across the membrane can. This is different from carrier-mediated diffusion. In carrier-mediated diffusion, we are going to allow only 1 or 2 molecules across at a time. So channel-mediated diffusion is like the door to a mall. Any number of people can move in and out of that door, whereas carrier-mediated diffusion is going to be like going to a movie. You can only get into the movie if you have a ticket. That ticket allows one person to move through the doors of the movie theater at a time. So we can get back to our different types of transport. So we have very thoroughly discussed diffusion. Diffusion can be simple or it can be facilitated. In facilitated diffusion, we can either use channel proteins, which allow a large number of a specific solute to cross the membrane according to its gradient, or we can use carrier proteins. Carrier proteins are going to transport molecules that are too large to fit through the membrane by itself. This is still going to be passive transport, so we are still moving substances down their concentration gradient. But with a carrier protein, we are going to move a specific number of a specific solute across the membrane at one time. Okay, so this is where it requires a ticket. I mentioned going into a movie theater, you have to buy a ticket to get in. Same thing with like riding the subway. Only people that have a ticket can go into the subway terminal. So carrier proteins are only going to move a specific number of solutes across the membrane at a time. Both channel proteins and carrier proteins need to be integral proteins, so they need to span the entire length of the membrane. Both of them are going to be material specific, so we are going to have a receptor site on our carrier protein that binds to a specific receptor. And then that binding on our carrier protein is going to cause the protein to change shape. And when the protein changes shape, it allows the molecule to pass across the membrane. So remember, we have specificity, one transport protein for one kind of substance. Our carrier-mediated transport is going to exhibit saturation limits. So the rate of transport depends on the number of transport proteins, not the amount of solute. And then also our carrier-mediated transport is going to exhibit regulation. So specificity, saturation limits, and regulation, meaning that we can alter the activity of our transport proteins using cofactors such as hormones. So we've got a specific receptor site for a specific molecule on our carrier-mediated transport. Our rate is controllable. So unlike simple diffusion, our cell can regulate the activity or the number of carrier and channel proteins available. The number of receptors is going to limit the ability of a cell to transport material across the plasma membrane, and the more receptors that we have available, the more substances that can be transported. Okay? So carrier-mediated transport can be passive. When carrier-mediated transport is passive, we call it facilitated diffusion. Facilitated diffusion moves substances across the membrane down that substance's concentration gradient. Carrier-mediated transport can also be active, and so we're going to use active transport proteins. These active transport proteins move substances against the concentration gradient, which requires energy.